Exploring electrostatic properties of incompatible polyelectrolyte blends through controlled synthesis. Hi, my name is Ashley Miranda, and I had the opportunity to complete a summer undergraduate research at Florida, also known as SURF. I worked under Dr. Neitzel in her polymer research lab. I was involved in the project that involves electrostatically stabilized microphases, specifically in the synthesis of polystyrene using Argit ATRP. Before I explain further, I would like to first start with a little bit about me, and then I would like to explain the overall basis of the project, and then move along into the synthesis. I attend Arizona State University in the beautiful and sunny Valley of the Sun in Tempe, Arizona. I am a rising senior, and I study material science and engineering. I grew up in Arizona, and while some people hate how hot it can get here, I am the opposite and enjoy the heat. Most of the year, we have great weather. So what is a polymer? Maybe you've heard of it. It's a class of material that is distinguishable by its long chain order. A polymer is when molecules, also known as monomers, are repeatedly linked together into a larger chain. This chain can be a homopolymer that is comprised of the same type of monomers linking together, or a copolymer that is comprised of more than one type of monomer. There can be various configurations with multiple monomers as well as varying architectures, such as the one shown. Why is this important? Well, copolymers provide the ability to benefit from the properties of multiple distinct polymers. Examples include better mechanical properties, stretch control, strength, etc., just to name a few. There are many unique properties that derive from the complex structure of copolymers. Due to these properties, various materials can be made. One example of this is spandex, which is used in synthetic fiber. In this project, though, the aim is to take two incompatible polyelectrolytes with different desired properties and attempt to electrostatically stabilize them in solution to then be able to study the unique properties formed if and when they self-assemble. Electrostatic stabilization occurs when molecules of opposite charges interact with one another to essentially cancel out each other's charge. On the left of the figure, we can see the mixing of the polycation and polyanion. Then the figure depicts the electrolytes becoming electrostatically stabilized in the microphase, which is a microscale portion of a solid. The desired result is that the mixing of the charged polyelectrolytes will drive them to self-assemble in charged microdomains layer by layer. But how do we get these polyelectrolytes? First, we must make the precursors that will eventually go through another reaction to create the polyelectrolytes. However, we must consider that we want to be able to control the way the precursors are synthesized. We want to control the molecular weight because for polymers, different molecular weights have varying properties. Another important parameter we want to control is the polydispersity, which is a way to measure how uniformly molecular weight is across all the polymers in a solution. The closer to 1, the better, as it indicates most polymers in a solution are pretty close to having the same molecular weight. The greater the value, the more dispersed the molecular weight is, which makes it difficult to study the unique properties that polymers have if you can't determine what molecular weight is causing that property. Argit ATRP is a type of radical polymerization that allows for the control needed. This summer, the group focused on synthesizing polystyrene that will then undergo another reaction to produce the polystyrene-rand-styrene sulfonate anion. The cation is something that will be focused on at a later date within the research group. ATRP stands for Atomic Transfer Radical Polymerization, which is a type of controlled radical polymerization. It allows for carbon-carbon bonding with a transition metal catalyst. If you remember, a polymer is a long repeating chain of monomers, and this reaction forms those bonds. It involves an initiator, a catalyst bound to a ligand, an oxidized catalyst bound to another ligand, propagating radicals, and the monomers that are being added to the chain. A cool thing about this reaction is that it is a reversible deactivation radical polymerization, meaning that the reaction can be revived after termination processes have occurred. There are also many types of ATRP reactions where different aspects of the reaction are manipulated, whether it be the concentration of catalyst, addition of radicals, addition of reducing agents, the use of zero-state copper instead, etc. In our case, we decided to use Argot ATRP, where a low concentration of catalyst is used in conjunction with a reducing agent to regenerate copper 1 from the irreversibly formed copper 2 in termination process. As seen in this figure, introducing a reducing agent allows for reviving the oxidized catalyst and allows to once again move the reaction forward for polymerization growth. This is especially attractive in industry as it reduces costs and is considered a green reaction. In our experiment, we decided to synthesize a polymer of about 20,000 monomers and used literature to determine parameters, which in our case allowed the reaction to occur for about 30 hours. Samples were taken intermittently throughout the reaction. Once the reaction was completed, we had to first remove other solutes in solution using alumina in a column. Then we were able to purify the polystyrene and methanol. In these clips, you can see the moment the solution falls into the methanol, it precipitates out into a purified polystyrene. We then collected the precipitate by drying it through a funnel. The next steps to the experiment will be characterizing the product that was made using nuclear magnetic resonance and size exclusion chromatography. NMR will confirm that polystyrene was made, whereas SEC will allow us to find the molecular weight. The future endeavors of the lab will consist of creating the other precursor for the cation to then be able to mix the polyelectrolytes and drive them to self-assemble in charged microdomains. This self-assembly will then be studied to determine the properties that will hopefully bring about new information that will be useful in the world of polymers. But research wasn't the only thing the SURF cohort got to experience. There were many planned trips where we got to bond and get to know one another. Some of my favorite activities were the St. Augustine trip, where we first got to meet everyone and had a blast on the beach. The Echetuckney Springs State Park, where we got to enjoy the beautiful clear waters of one of the many springs Florida has to offer. It even rained as we were floating down the river. It was pretty magical. But my favorite trip of all was the trip to Kennedy Space Center, as it's always been my childhood dream to see bits and pieces of American history in the space war. I got to see real-life artifacts that were actually in space. I won't ruin the surprises, but just know that it was absolutely worth it. In my time here, I was also given the opportunity to join the Semiconductor Readiness Organization, also known as SCRO, where we were introduced to micro and nanofabrication firsthand. We were encouraged to tinker with the process parameters to better understand the theory behind the steps. It was very hands-on, trial and error approach, and I have learned a significant amount of what happens in chip processing. After this amazing experience, I plan to go back to my home university, where I will finish my last year and prepare for fall graduate school applications. I have learned much valuable experience of what it's like to work in a lab, especially in a new lab, and all the hard work that goes into jump-starting the research group. I hope to one day conduct research in thin film, where I can hopefully become an expert in using deposition techniques. I would like to say thank you to Dr. Angelica Neitzel for welcoming me into her lab for the summer and giving me the opportunity to learn about polymer science. I would like to thank Dr. Gilla for inviting me to join SCRO and providing me with the hands-on experience in a field that I would like to one day enter. Lastly, thank you to Mike and Ashley for putting the SURF program together and giving us the experience of a lifetime. Thank you.